So yeah, thanks to Andy and the other organizers for inviting me to this. So as Walt said, this is something of a two-part presentation. He's given the first and I'm going to give the second. So Andy said that the title, as it were, of this panel was the nature and uses of reverse mathematics. So in some sense, I'm going to talk in two parts. Firstly, about the nature of reverse mathematics, and then about its uses. So the nature here is this notion of set existence. And I'm going to talk a little bit about what I take to be a kind of standard view, maybe even something that people take for granted, which is that the significance of reversals in reverse mathematics lies in demonstrating the set existence principles that are necessary to prove theorems of ordinary mathematics. And of course, the locus classicus for this is Steve Simpson's book. Page 2, the main question of subsystems of second order arithmetic: which set existence axioms are needed to prove the theorems of ordinary non-set theoretic mathematics? Of course, you can find expressions of this sort throughout the literature, I think very much influenced by Steve, but also just by the community's sense of what it's doing. But I think there's a kind of reasonable question to be asked here, which is, what are set existence principles? So there's a kind of naive view where we just say, ostensibly, well, recursive comprehension is a set existence principle, weak Koenig's lemma is a set existence principle, arithmetical comprehension is a set existence principle, and so on. But presumably, if we want to provide a philosophical account of what's going on in reverse mathematics, we want to say something a bit more than that. We want some kind of analysis of the concept of a set existence principle, ideally. I'm not sure that we have one, I'm not sure we can have one, but I think that's a reasonable thing to at least try and aim for. And this is something that Sean Walsh and Walter Dean kind of flagged in their 2017 paper, that this was an issue, and they offered a kind of answer based on the historical importance of particular set existence principles as kind of cashed out in the big five subsystems. But I think it would be nice to at least try and aim for something a bit broader, especially in light of the fact that the subject has really changed a lot in the last 20 years, as Damir and Carl alluded to when they talked about their book. We have the zoo, we have things like RT22, we have CO, we have ADS, we have all of these things. And presumably we're thinking of these as set existence principles too, if we're thinking of reverse mathematics in these terms. So what we want is an analysis that is non-trivial. It doesn't say that every sentence in the language of second order arithmetic is an axiomatization of set existence principle. We want it to be comprehensive, so it should include everything that we think of as a set existence principle. And it should be, in some sense, conceptually unified. We should have one reason for saying that these things are all set existence principles. We shouldn't just be saying, well, I have this reason for thinking that weak Koenig's lemma is a set existence principle, but this other reason for thinking that, say, arithmetical comprehension is a set existence principle. So then a natural starting point is just to think, well, maybe comprehension axioms are our starting point for set existence. We can see how these are set existence principles in a kind of prototypical way. They say there exists some set with this definition of a particular complexity. And we can think of maybe the principle as being the whole scheme rather than just particular instances. But nonetheless, we can see that there are easy counterexamples, things like weak Koenig's lemma, things like arithmetical transfinite recursion, which are not equivalent to any sub-scheme of the next comprehension scheme up, as it were. So weak Koenig's lemma is not equivalent to any instance of arithmetical comprehension, for example. And it's in this sense that it's a kind of counterexample to this initial view. Then you might think, okay, weak Koenig's lemma, arithmetical transfinite recursion, we can see these are equivalent to certain separation schemes. So then maybe we can classify them more broadly and think set existence principles are comprehension principles and separation schemes. Maybe we can even come up with a way of unifying them so that we can satisfy this desideratum of conceptual unity. And there's a way that one can do this. But then, again, this leaves something out. So we're violating this comprehensiveness requirement. So we're leaving out things like weak Koenig's lemma, things like RT22, and all of the other residents of the zoo don't fit into this picture. So then, there's this nice quote from Kreisel that I'm going to start with, talking about another approach. When I was working on this a few years ago, I didn't come across this quote until after I'd written and got published the paper I wrote on it, which is kind of frustrating. So I feel like it should really have played a part in this. But Kreisel says that a little care shows, in effect, that the bulk of current mathematical practice, only very weak closure properties are used. So the bulk of current theorems generalize. Whenever the notion of set is used explicitly or implicitly, it can be interpreted to mean set of a, so to speak, elementary, meaning arithmetical or hyperarithmetical or something like this, collection of sets satisfying the particular weak closure conditions. So what Kreisel is saying is something like, we don't have to think of some theorem as being true in set theory, true of the notion of set and true in V, but true just in some subuniverse where we just have some particular weak closure condition applying. And obviously, the particular closure condition that applies will vary depending on the theorem. And Kreisel goes on to say exactly this and connect it to precisely these kinds of computability theoretic hierarchies. And these kinds of sentiments are very widespread, so you can see them in this Pfefferman 1964 paper that Steve alluded to, and also I think that Walt alluded to. So Pfefferman says something along these lines as well. And then some more recent papers. These ones I just pulled out of my paper as citing examples of people holding something like this view. So Shaw 2010, Derace, Japarov, Hurst, Miletti, and Schaefer 2016, Zhang, Slayman, Yang 2014. So they all say something along these lines. That what reverse mathematics is doing is somehow studying closure properties of the set of reals or power set of the natural numbers. And holding a view like this also helps make sense of the special role that omega models in particular play, because here we're just fixing the first order part of the model, and then we're varying the second order part and say, okay, it can be whatever you like, any class of sets of natural numbers that you like, as long as it satisfies this particular closure condition. So what do I mean when I say a closure condition? Well, I just mean saying that the power set of the natural numbers is closed under some relation phi. So given some set of natural numbers, there's some other set that stands in this relation phi to it. And we can think of all of these principles as being of this form. And in fact, we can just read off the logical form from this and say, well, clearly any pi1,2 sentence is going to axiomatize a closure condition. And in general, it seems pretty reasonable to say, well, this phi could have higher complexity than arithmetical. So any pi1n sentence with n greater than or equal to 2 is going to be an axiom expressing some closure condition. But obviously, here we're kind of flirting very closely with violating one of these other conditions. So I talked about comprehensiveness, and I talked about unity, but there's also this kind of requirement of non-triviality. We don't want it to be the case that every sentence expresses a closure condition or a set existence principle, because otherwise it seems like the concept is empty. It's not doing any work if it's just everything. And then we're just saying, what are we doing in reverse mathematics? We're proving equivalences, and then it doesn't really give any kind of substance to what's going on. So then I have this additional condition that I had in this 2019 paper, that any pi1n sentence axiomatizes a closure condition just as long as it's not equivalent to a sigma 1n sentence or any sentence of lower complexity over some suitable base theory. And this is obviously an informal notion, right? Because this notion of a suitable base theory is going to vary depending on what the statement is. And so here, I'm just going to sort of reason on a kind of case-by-case basis. I'll give you one example. So the statement, the conjunction of weak Koenig's lemma and zero jump exists, we shouldn't think of this as being a closure condition, because while weak Koenig's lemma is a closure condition, zero jump exists just saying that one particular object exists. It's not saying the universe is closed under the jump. And we want a way of ruling this out. So then what's the way to rule it out? Well, work in WKL0, and then we can prove that this statement is equivalent to a sigma 1,1 statement, and therefore it's not a closure condition. One might then have a reservation that suddenly we're not capturing all of the set existence principles anymore, right? And you might think, okay, zero jump exists, that's a set existence principle in a fairly straightforward way. So my view is actually committed to saying that's wrong, and that the word principle is somehow doing some work. It's not just a set existence statement saying that some set exists, but it's something more general, more powerful, in the same way that we think that the Bolzano-Weierstrass theorem is a theorem, but if we state it for some particular sequence, then it doesn't really count as a theorem anymore. It's just an instance of a more general theorem. And similarly, I'm taking the line that it's these pi 1n statements that are the principles, and then the sigma 1 n minus 1 statements are just instances. Okay. So that's already dealt with a couple of problems that one might have with this view. I think there are others that are pretty reasonable and can be pressed on it. One is just that this doesn't account for the whole practice of reverse mathematics. This, I think, is slightly less of a problem, but maybe worth going through anyway. Obviously, equivalence is to well-ordering principles. So if you prove, say, an equivalence to the well-ordering of omega to the omega, or omega to the omega to the omega, this is a pi 1,1 statement. So this is not going to count as a closure condition, and not going to count as a set existence principle on this account. I personally don't think this is problematic, because I don't think that those are set existence principles, because in some sense they're set non-existence principles. You're saying that there exist no infinite descending sequences in this ordinal. So I think that these things are a part of reverse mathematical practice, but they're a different kind of principle. So really what we have to do is restrict the view and say reverse mathematics is not only about finding these set existence principles that underpin ordinary mathematical theorems. It's about finding principles in general, and some of these, perhaps most of them, are set existence principles, but there are obviously exceptions. Equivalences to induction are an obvious further example. So, sorry, I'll try and move the cursor off. Can you actually see this bottom bit? Yeah. All right, well, anyway, what it says is that, it doesn't account for statements that are arguably set existence principles, but are not axiomatized by a pi 1n greater than or equal to 2 statement. And the obvious example here is like bounded sigma 0, 1 comprehension. So existence of finite sets. And Steve, in his book, I think I didn't put in the page reference, but in any case, it's in chapter 2, argues that this bounded sigma 1 comprehension is a set existence principle. So the existence of finite sets is a set existence principle, and therefore, going back to this main question, what set existence axioms are needed to prove the theorems of ordinary non-set theoretic mathematics, we can include bounded sigma 0, 1 comprehension in there, and therefore we can include the induction principle for RCA 0 in our collection of set existence principles. So in my view, taking set existence principles to be closure conditions, this is ruled out, right? Because this is really another pi 1,1 statement. So I think this is something that maybe one can have more of a disagreement about, whether induction is really a set existence principle, perhaps in some kind of disguise. But I think it's clear that at least it's not a closure condition in this way. Not in the way I was thinking of anyway. But one might still think this is some kind of closure condition, but it's just giving us closure under finite sets. I guess one thing I would say is that going back to the point I made about omega models, of course, things like this, if we just look over omega models, so where we have full induction, of course, these things are ruled out. They're always going to be true. So then I think that if you want to push back and say, well, these things really are set existence principles, then you have to have a really quite different view that doesn't assign this special status to omega models. So, but this is a kind of complicated thing, so I'm happy to discuss this, either in the panel or afterwards. Okay, so that was the nature of reverse mathematics. Now I'm going to move on to talk about its uses. So I'm going to start off with a few observations about mathematics in philosophy. So one thing to say here is that a lot of arguments in what I'm going to call core philosophy, in analogy with core mathematics perhaps. So here, metaphysics, epistemology, ethics, political philosophy, perhaps philosophy of mind, philosophy of language. Many of these arguments, especially nowadays, rely on mathematical theorems. I mean, in some sense, this is surprising. Don't have this traditional view of philosophy, at least philosophy as a discipline as a whole, as being deeply invested in mathematics. Obviously, mathematics serves as a model in epistemology that we want to think about the rigorous deduction as being a way of attaining knowledge, perhaps the paradigmatic way of attaining knowledge, going all the way back to Plato. But nonetheless, the idea that serious mathematics is actually going to be playing a role in philosophy is maybe a little alien, but nonetheless, it is a substantive and going concern in much of mainstream core philosophy. So when I say that arguments in core philosophy rely on mathematical theorems, what I mean is that these theorems appear as premises in the arguments. So for example, there's an argument or a series of arguments in epistemology, formal epistemology, called Dutch book arguments. And basically, in these Dutch book arguments, one argues that an agent ought to have, that is rationally required to have, a set of credences, that is, degrees of belief in certain propositions that accord with the probability axioms, or other principles that are being argued for. So principles like conditionalization. But the most classic one is this view that the degrees of belief that an agent has in order to qualify as rational should be probabilistically coherent. And the argument for this is based on the fact that if an agent doesn't have degrees of belief that are coherent in this way, then they are vulnerable to these so-called Dutch books, to basically bets where they will, or books of bets where they will always lose. So this is using some mathematics to say that if you don't obey the probability axioms, then you're going to be vulnerable to these Dutch books. So that's a very clear and explicit example of a mathematical theorem appearing as a premise, an explicit premise, I would say, in such arguments. Obviously, there's some kind of difference here between the mathematical premise and, say, the philosophical premises of these arguments. So the philosophical premises are going to be about a certain kind of view of what rationality involves and what the normative epistemic requirements are on agents, what kinds of arguments should have normative force in these contexts. And people argue back and forth about this. But you don't see philosophers saying, well, the Dutch book theorem is false and therefore the argument doesn't go through, right? So the mathematical principles are privileged, but nonetheless, they are premises of these arguments. And so their truth is needed in order for the argument to be sound. So that's the first observation, and I'm going to come back to this one. The second is that anti-realist and more broadly reductivist views about mathematics are common amongst these core philosophers. So you'll see a lot of people also in philosophy of mathematics, but very much in these core areas of philosophy, who argue in favor of nominalism, in favor of fictionalism, maybe sometimes also in favor of something like logicism. And the broad picture here is that these views are ones on which we can eliminate all of this horrible abstract ontology of mathematics. You know, there's something weird and perhaps dangerous about this stuff, and we should get rid of it. We should be hard-nosed physicalists. Only physical objects exist. And maybe mathematics is useful as some kind of abstraction, idealization, but it's not real. And so we should try and get rid of it if we possibly can. And they'll go through all kinds of contortions trying to do this. And I want to suggest that these first 2 points are somewhat in tension with one another. So there's a kind of obvious tension. And of course, there will be many complicated answers as to why they're not in fact in tension from these people. But I think that Walt and I have a fairly sophisticated story about why there really is some kind of tension here. So the third point I wanted to make here was just that in a lot of these arguments about these everyday notions, so I was talking about degrees of belief. I mean, this seems kind of outre, maybe, or recherché. It's not an everyday notion, but I think really it is an everyday notion, or should be. You know, that if we're flipping a coin, then we have degree of belief 1/2 that it'll land heads, degree of 1/2 that it lands tails. So this is a kind of, we just assign probabilities, perhaps not explicitly, but implicitly, to certain outcomes occurring. We think that certain things are likely, and therefore we behave as though they're going to happen. We think other things are unlikely, and we behave as though those things aren't going to happen. So these kind of assignments of probabilities do guide our behavior. So they are everyday notions in this sense. And so when philosophers reason about these everyday notions and use mathematics to do so, they are, of course, in a bit of danger that there's going to be some kind of excess idealization involved. So, for example, this problem of logical omniscience. So in epistemology, we want to have perhaps axioms for knowledge. I'm going to say, well, if you know something and it's true, knowledge is factive. If maybe you want to be an internalist and say, if you know something, then you know that thing. So we're going to have principles about knowledge. But what most of these things end up doing in some way, and obviously the thesis about probabilism in formal epistemology is an example of this, what most of these things do is build in this assumption of logical omniscience. So if there's some logically valid sentence, that is one which can be derived from no premises or which is true in all structures, then we know that. Right? So obviously we don't. We're extremely limited, finite beings. We don't know all of the logical consequences of some set of axioms. But nonetheless, this principle of logical omniscience is built in, perhaps as a slightly embarrassing idealization, into many of these epistemological projects. And people will either say, well, we're not interested in just the logical statements, and we're really talking about the non-logical statements, and so that's where our focus is, and this is just a kind of idealization to get our system going. Or maybe they'll be a bit more embarrassed about it and try and get rid of it. But this is a problem, this kind of excess idealization. And I want to suggest that the analysis I'm going to put forward offers a kind of way of looking at idealization in these fields, just as it offers an analysis of when arguments rely on mathematical theorems and what mathematical theorems precisely they are relying on. So this is our indispensability program, or reverse philosophy. And the idea is just that we're going to assess the use of theorems in philosophical arguments in metaphysics, epistemology, philosophy of logic, philosophy of language, political philosophy, ethics. And the way we're going to do it is going to be using reverse mathematics. So now we've moved from the nature of reverse mathematics to something that reverse mathematics can contribute to philosophy. And I'm going to talk about all of this in much more detail on Thursday, but just to give you a quick sketch of how it's supposed to go, the idea is as follows. So suppose I've got a theorem phi, and I use this in philosophical argument A. So I'm using it as a premise in this argument. So then the methodology is as follows. We formalize that theorem phi in the language of second order arithmetic. And of course, this is typically possible because the everyday mathematics that's used in philosophy usually comes from a few fairly limited areas. It comes from discrete mathematics, from probability, say from mathematical economics. That's what I'm going to be looking at on Thursday. And I should say that, much of the time, thanks to all of the work done over the last, let's say, 40 years, we don't even need to do anything. We don't need to formalize it because it's already been done, which is great. And then we can assess the strength of that theorem using reverse mathematics. So we can see, maybe reverse mathematics proves that theorem phi is equivalent to principle P. So for example, say you're reasoning about these Dutch books, you use some kind of separating hyperplane argument, and therefore we can get some kind of reversal to weak Koenig's lemma. And sometimes the reversal is off the shelf, it's something that's already known, and sometimes it's not known, and then we have more work to do. But as I'm going to talk about more on Thursday, this also means that this program also offers the prospects for new sources of reversals and problems for the reverse mathematics community. So sort of pulling back a level, what we've done by this point is show that this principle P is a kind of suppressed premise of this argument. So the argument perhaps explicitly uses the theorem, but of course, because the theorem implies the axiom, then the axiom itself is entailed by the soundness of this argument. And we can then ask, what does this mean for proponents of this argument? And what does it mean for opponents of this argument? Because in philosophy, you're always going to get people on both sides. Even if it's a very small set on one side or the other, there will always be people on both sides. So one thing we might ask is, well, is this principle P accessible to proponents of this argument? So suppose you're a nominalist, but you're trying to push some argument that relies on maybe something highly non-constructive. Then it seems, at least for certain varieties of nominalism, seems implausible that they would be able to nominalize this principle. So for example, Hartree-Field has this program of basically reducing mathematics to physics, or at least some version of physics, where we take space-time points as our basic objects, and then we have space-time regions, maybe even quite complex ones, maybe like Borel space-time regions. But then, maybe we see in an argument from, let's say, a nominalist, something like the Cantor-Bendixson theorem being used, then it looks like even a system that admits of Borel space-time regions is not going to be able to reach this. So that's one thing about this accessibility. And another way of thinking about accessibility here is just to think that if someone is using an argument and it entails some principle P, whether that's weak Koenig's lemma, arithmetical comprehension, or whatever, we have a kind of indispensability argument. So we should say they think that the premises of their argument are true and the argument is valid. It's a sound argument. So therefore, those premises entail this axiom. So they should also be committed to this axiom. And presumably, for their argument to work, the mathematical premise has to be just as true as the philosophical premises. So we have an argument that the mathematical principle that's underlying this theorem is thus indispensable to this argument, or maybe to the view behind this argument, or to the person putting the argument forward, but nonetheless some kind of indispensability of mathematics. And again, this is something I will cover in more detail on Thursday, and talk a bit more about indispensability as a kind of issue in philosophy of mathematics. A second thing that one can do once one has this analysis in hand is look at what the opponent's reaction can be to this argument and the fact that it relies on this mathematical principle. So suppose I don't like the Dutch book argument. I don't think that we are rationally required to have probabilistic credences. I could just say, well, your argument requires this separating hyperplane theorem, and this is equivalent to Weak-Koenig's lemma, but I only think that recursive sets exist. And so this theorem is false. And therefore, I don't have to accept your argument. So this is a new resource for people who want to object to these arguments. Before, they could only object to the philosophical premises, but this offers a way that, at least in some cases, people can object to the mathematical premises too, because having this kind of precise analysis of what exactly is in the argument mathematically allows these kind of moves to be made. And then finally, going back to this third point about excess idealizations, a natural thing to then think is to say, well, if the principle that is implicit in this argument entails the existence of highly complex sets, say hyperarithmetical sets or pi-1-1 sets, whatever it might be, non-computable sets even, just as simple as that, that might be enough to tell us that this argument, this way of reasoning about a certain domain is too idealized. They have the philosophical argument is baking in kind of mathematical model that doesn't really capture what's possible in the domain of application. So maybe the domain of application is finite human agents, or even finite agents that are not necessarily human. Maybe, they're infallible in all of their reasoning and they can reason as long as they like, but still they can't do non-constructive mathematical operations. And if you have some principle involved that involves the existence of non-computable sets, then this just may show that this model is wrong. So again, we could think about this argument, this Dutch book argument, in this way. You can think about it that if I'm objecting to this Dutch book argument, one of the grounds I might have is that being able to set all of my credences, perhaps for an infinite set of propositions, in such a way that I satisfy the probability axioms, this might require me to compute some non-computable set, right? And therefore, maybe this is a bad model that, at least for perhaps certain classes of problems where maybe we want to set degrees of belief in some infinite set of propositions or possible events or something, maybe in those cases, it's just not reasonable to expect agents, not even, even quite idealized agents, agents who can act like Turing machines. It's not reasonable to expect them to behave probabilistically because they're just not able to compute it. And obviously, always implies can, so can't implies is not obliged to. So I'm just going to finish up with this table of reversals and implications. And on the left, we've got various kinds of philosophical arguments or philosophical positions. In the middle, the principle that's involved in these arguments, and then the corresponding theory. And this is just from our survey of the literature. I want to call out a few things in particular. So on Thursday, I'm going to talk about this squeezing argument. So this is Kreisel's squeezing argument for validity. So the idea being that the informal notion of validity of valid reasoning is squeezed between formal derivability and logical entailment, that is the Tarski notion of truth in all structures. And of course, the squeezing is via the completeness theorem for first-order logic, and therefore requires Weak-Koenig's lemma. I'm going to talk a little bit about the Sorites paradox, in particular a continuous variant of this. And this requires the existence of least upper bounds. So this is just the Bolzano-Weierstrass theorem or something similar. And so that's ACA 0. And then I'm going to talk a bit more extensively about whether democracy is possible. Actually, I'm not going to talk that much about the democracy part, but I'll talk a little bit about it. But I'm going to talk about social choice theory, Arrow's theorem, infinitary variants of Arrow's theorem, and I have some results about this and how results relating to this require the existence of non-principal ultrafilters, and therefore this gives us arithmetical comprehension. Okay, so I'm going to finish there. Thanks.
Right, the idea of the panel was that we could have some presentations that would give us something about which we can talk, but really the idea was we have this subject, what is reverse mathematics, what is it good for, and I'm interested in hearing from everyone about what you think about this. So what do you think? We've been doing this now for a while. Why? What is it anyway?
So you said you were going to stop the recording. I didn't